In this section, we will study about the basics of failure by creep mechanism. First, let us study about what is creep. An important characteristic of high temperature strength is that it must always be considered with respect to some time scale. The tensile properties of most engineering metals at room temperature are independent of time for practical purposes, which means it makes little difference in the results if the loading rate of a tensile test is such that it requires 2 hours or 2 minutes to complete the entire test. But at elevated temperature, the strength becomes very much dependent on both the strain rate and the time of exposure. A number of metals under these conditions behave in many respects like viscoelastic materials. Thus, this time-dependent increase in length of a metal subjected to a constant tensile load at an elevated temperature is called creep. Now, let us come to the homologous temperature. A strong time dependence of strength becomes important in different materials at different temperatures. Now, what is high temperature for one material may not be so high for another. To compensate for this, temperature often is expressed as a homologous temperature, which is the ratio of the test temperature to the melting temperature on an absolute temperature scale. Now, generally, the creep becomes of engineering significance at a homologous temperature greater than 0.5. Next, let us know about the test to evaluate the different creep characteristics. Now, special tests are selected to evaluate the strength or performance of materials in different kinds of elevated temperature service on the basis of the time scale of the service which the material must withstand. For example, an elevated temperature tension test can provide useful information about the high temperature performance of a short-lived item. For example, a rocket engine or missile nose cone. But it will give only the most meager information about the high temperature performance of a steam pipeline which is required to withstand even 1 lakh hours of elevated temperature service. Now, the creep test measures the dimensional changes which occur from elevated temperature exposure, while the stress rupture test measures the effect of temperature on the long time load bearing characteristics. So, this is all about the definition of creep, the homologous temperature, and the creep test. Example of time dependent mechanical behavior is anelastic behavior and elastic after effect. For the discussion of elastic behavior, it is generally implicitly assumed that elastic strain is a single valued function of stress alone. Now, this is a valid assumption for the engineering analysis of metals by the theory of elasticity. However, under some circumstances, there is a time dependence to elastic strain, which is called anelasticity. In this figure, we can see an elastic strain of E1 is applied to an inelastic material. With increasing time, the strain gradually increases to a value of E2, the completely relaxed strain. Now the amount of inelastic strain becomes E2 minus E1. If the load is suddenly removed at time is equal to T1, the material undergoes an immediate elastic contraction equal in magnitude to E1, as shown in this figure. And with further passage of time, the strain decays to 0. This behavior is called an elastic after effect. Let us now study about the change in temperature of a material with respect to strain. If a material is loaded to an elastic stress so rapidly so that there is no time for any thermal effects to equilibrate with the surrounding, the loading is done at constant entropy and under adiabatic conditions. Now for such uniaxial loading, change in temperature of the material with respect to strain is given by this particular equation, where Vm stands for the molar volume of the material, alpha is the coefficient of linear thermal expansion, E indicates the isothermal Young's modulus of the material, T is the absolute temperature, while Cv stands for the specific heat at constant volume. Now, in this equation, since alpha is positive for most of the materials and other terms are also positive, it indicates that an adiabatic elastic tension actually decreases the material temperature, while an adiabatic compression increases the temperature. However, these temperature changes associated with the thermoelastic effects are usually very small. In this section, we will study about the adiabatic and isothermal stress-strain curves. If a specimen is stressed elastically at a very slow rate so that it is in thermal equilibrium with its surroundings, it will actually follow a path A, B, C as shown in this stress-strain curve, and the path C, B, A on unloading. However, if the specimen is loaded rapidly to stress sigma C so that there is no time for thermal equilibration with the surroundings, the temperature of the specimen will decrease a small amount and the specimen follows the path A C dash as shown in this figure. The strain that accumulates in the specimen will be only EA instead of the strain EI that would result from an isothermal path. Also, the elastic modulus under dynamic or rapid loading condition is higher than the modulus under static or slow loading condition. Now, with the passing of time, the specimen will warm up and elongate due to thermal expansion along the path C'(C), as we can see in this figure. If now the load is removed suddenly, the specimen will follow the adiabatic path C', and the specimen temperature will now rise a small amount. With the passage of time, the specimen transfers heat to the surroundings and the strain decreases by thermal contraction along the path C double dash A. Thus, the result is a closed hysteresis loop A, C dash, C, C double dash and A. So, this is the adiabatic stress strain curve, which may be called as idealized, and this A, B, C is the isothermal stress strain curve. However, in an actual material where the specimen is loaded and unloaded in a continuous cycle, the elastic hysteresis loop will look like as in this particular figure. As we can see that this is the elastic hysteresis loop in a practical condition. Although the area included within the hysteresis loop may be very small, it can be an important parameter for a material subjected to the rapid vibration, since the total energy dissipated in a given time period is the product of the hysteresis area per cycle times the number of cycles. From an engineering point of view, this elastic hysteresis leads to the generation of heat and the damping of vibrations. Now, the area under this hysteresis loop will be a function of the frequency at which the stress is applied and removed. If the frequency is very low, the cycle will be almost completely isothermal, and the area enclosed by the hysteresis loop will be very small. On the other hand, at a very high frequencies, the loading and unloading paths are almost completely adiabatic. And once again, the area enclosed by the hysteresis loop is very small. However, there will be some frequency intermediate between these extremes for which the area of the hysteresis loop is a maximum. In this section, we will study about the creep curve. Over here, the first figure illustrates the idealized shape of a constant load creep curve and its different stages. In this figure, we can see the y-axis is represented by the creep strain, while the x-axis is represented by time. Now, the slope of this curve, that is d epsilon by dt, or the strain rate, is actually referred to as the creep rate. If we see the creep curve, following an initial rapid elongation of the specimen or this instantaneous deformation as denoted by epsilon dot, after that the creep rate decreases with time. Then the creep rate reaches essentially a steady state in which the creep rate changes little with time, and finally the creep rate increases rapidly with time until fracture occurs at this point. Thus, it is natural to discuss the entire creep curve in terms of its three different stages, that is the primary, secondary and tertiary creep. It should be noted that the degree to which these three different stages are readily distinguishable depends strongly on the applied stress and temperature. Let us now discuss about the different stages of the creep curve in detail. The first stage of creep, known as the primary creep, represents a region of the decreasing creep rate as shown in this figure. Now primary creep is a period of predominantly transient creep in which the creep resistance of the material increases by virtue of its own deformation. For low temperatures and stresses, as in the creep of lead at room temperature, primary creep is the predominant creep process. Next, the second stage of creep, known also as the secondary creep, as shown in this figure, is a period of nearly constant creep rate which results from a balance between the competing processes of strain hardening and recovery. For this reason, secondary creep is usually referred to as the steady state creep. As we can see in this figure, the creep rate is minimum over here and it is called a steady state creep. The average value of the creep rate during secondary creep is called the minimum creep rate. Next, the third stage or the tertiary creep mainly occurs in constant load creep test at high stresses and at high temperatures, as we can see in this figure. Tertiary creep occurs when there is an effective reduction in cross-sectional area either because of necking or internal void formation. Third stage creep is often associated with metallurgical changes such as coarsening of precipitate particles, recrystallization or diffusional changes in the phases that are present. Over here, the second figure gives us the variation of creep rate with respect to the total strain. Here we can see in the first stage, that is the primary creep, the creep rate is decreasing with time, and then in the second stage or secondary creep, it is a steady state creep, so the creep rate is nearly constant, and in the third stage, that is the tertiary creep, the creep rate is again increasing before rupture. So these are the basics about the constant load creep curve and its different stages. In this section, we will learn about the constant stress creep curve. Here, in the first figure, the red line denotes the constant load creep curve, while the dotted line indicates the constant stress creep curve. The second figure represents the different components of a typical constant stress creep curve. Now, in case of an engineering creep test, it is usual practice to maintain the load constant throughout the test. Thus, as the specimen elongates and decreases in cross-sectional area, the axial stress increases. The initial stress which was applied to the specimen is usually the reported value of the stress. Methods of compensating for the change in dimensions of the specimen so as to carry out the creep test under constant stress conditions have been developed throughout the years. When constant stress tests are made, it is found that the onset of stage 3 is greatly delayed, as indicated by the dotted line in this figure. In engineering situations, it is usually the load but not the stress that is maintained constant. So, a constant load creep curve is more important. However, fundamental studies of the mechanism of creep should be carried out under constant stress conditions. Next, we come to the Andre's pioneering work on creep, which had a considerable influence on thinking of this particular subject. He considered that the constant stress creep curve represents the superimposition of three separate processes. The first one is a sudden strain which results from initial applying of the load. The second component of the creep curve is a transient creep with a creep rate decreasing with time. And the third component is the viscous creep, where this is a constant rate creep component, or the creep rate is constant with time. The superimposition of all these creep processes, that is the sudden strain, the transient creep and the viscous creep, gives us the constant stress creep curve as shown in this figure. Andre found that the constant stress creep curve could be represented by an empirical equation as shown over here. In this equation, the epsilon is a strain in time t, epsilon dot is the instantaneous strain on loading as shown in this figure, and beta and k are constants. So, this is termed as the Andre's empirical equation, which actually represents the constant stress creep curve. So, these are the basics about the constant stress creep curve and its different components. In this section, we will learn about the effects of stress and temperature on the creep curves. Here in this figure, we can see that the lowermost curve is a very flat one, where the creep is not so significant because the homologous temperature is very low. Now above this particular curve, we get different creep curves at different values of stress and temperature. Over here, the temperature increases from T1 to T2 and then from T2 to T3, whereas the stress value increases from sigma 1 to sigma 2 and then from sigma 2 to sigma 3. Now, with increasing stress or temperature, we can get three significant observations on the creep curves. Firstly, with increasing stress or temperature, the instantaneous strain increases. Secondly, with increasing stress or temperature, the steady state creep rate increases. And thirdly, with increasing stress or temperature, the time to rupture, that is, the rupture lifetime, decreases. So, this explains the influence of stress and temperature on the creep curves. It is important to differentiate between a creep test and stress rupture test. A creep test emphasizes on precision determination of strain, particularly the minimum creep rate. Generally, the creep test is performed at relatively low stresses to avoid the tertiary stage of creep. Total strain is often less than 0.5%. Creep tests are frequently conducted for periods of 2000 to 10,000 hours. Now, stress rupture test is similar to creep test, but unlike creep test, a stress rupture test is always carried out up to the failure of the material. Now, total strain may be as high as around 50% for the stress rupture test. Therefore, very simple strain measuring devices like dial gauges can be used in experiments. Higher loads are used for stress rupture test, therefore the creep rates are also higher. Higher stresses and creep rates cause the metallurgical structural changes to occur at shorter time durations than would be observed generally in case of the creep test. Therefore, the stress rupture test can usually be terminated within 1000 hours. From the application point of view, it is particularly well suited to determine the relative high temperature strength of new alloys for jet engine applications. Further, for applications where the creep deformation can be tolerated, but the fracture must be prevented, it has a direct application in design. In this section, we will discuss about the method of plotting the stress rupture data. Here in this figure, we can see that the applied stress is plotted against the rupture time on a log-log scale. The basic information obtained from the stress rupture test is the time to cause failure at a given nominal stress for a constant temperature as shown in this figure. Now, from this figure, it is revealed that the rupture time gradually decreases with the increase of stress level at different given temperatures as shown in this figure. On the other hand, with the increase of temperature, the rupture stress gradually decreases. The elongation and reduction of area at fracture are also determined. If the test is of suitable duration, it is customary to make elongation measurements as a function of time, and from this to determine the minimum creep rate. A straight line will usually be obtained for each test temperature as shown in this figure. Now, for each straight line, we can observe a change in slope. Changes in the slope of the stress rupture line are due to the different structural changes occurring inside the material. Example like changes from transgranular to intergranular fracture, oxidation, recrystallization, and grain growth. It is important to know about the existence of such instabilities because serious errors in extrapolation of the data to longer times can occur in case they are not detected.